Welcome to this explainer. Look, today we're diving straight into the completely chaotic, totally fascinating world of resilient distributed systems. We're going to unpack exactly how to architect, manage, and secure a massive system using microservices, gateways, and the underlying physical cloud infrastructure. If you've ever wondered how the world's biggest platforms stay online when things go inevitably wrong, you are in the right place. Let's just start by destroying the myth of the perfect system. Seriously, read the quote on your screen right now. The goal is not to prevent failures, but to contain them. Because let's be real, in a distributed setup, networks are gonna drop. Servers will crash. Dependencies will just hang for absolutely no reason. A truly great architecture doesn't pretend it can magically prevent these things. It expects them and it isolates them. Here's our roadmap for the explainer today. We're covering the distributed system challenge, the front door with API gateways, directing traffic via load balancing, data consistency and sagas, surviving network failures, and finally, the cloud bedrock. Let's get right to it. All right, section 1, the distributed system challenge. So how do we actually contain the chaos? Well, a well-designed system isolates failures using these exact tools. Instead of letting one sluggish database completely tank your entire application, you throw in a circuit breaker to stop the bleeding. Use retries with exponential backoff for those annoying temporary hiccups. But here's the kicker. You can't just build this and cross your fingers. You have to rigorously test it. In .NET, we use libraries like Poly or Simi to literally inject faults on purpose. We break things intentionally just to make absolutely sure the system either bounces back automatically or fails fast with an error that actually makes sense. Moving right along to Section 2, the front door, also known as API gateways. Think about a user interacting with your app. There is absolutely no way they should be trying to navigate your messy, complex web of 50 different backend microservices on their own, right? Instead, you put an API gateway right at the front. It acts like a highly intelligent traffic cop. The client makes one simple call and the gateway does the heavy lifting, routing that traffic perfectly to the right specialized service, whether that's your catalog, your shopping cart, or your billing system. By dropping this gateway into your architecture, you drastically clean up the client interface. Whether you're using Netflix Zool in a Spring Boot environment or a native .NET equivalent, giving your clients one single entry point is a massive game changer. It means you can centralize all that messy cross-cutting stuff. You manage your security rules, log every single incoming request, and handle authentication all in one central spot, way before the traffic ever touches your internal user or order services. Which brings us to Section 3, directing traffic, specifically load balancing. Okay, so once requests actually make it through the front door, we have a new problem. We have to make sure no single instance gets totally overwhelmed. When we look at modern load balancing options, YARP, which stands for Yet Another Reverse Proxy, is incredibly appealing, especially for .NET developers. Why? Well, compared to a C-based tool like Nginx or a locked-down, fully cloud-managed Azure gateway, YARP lets you write extensive, highly custom routing and load balancing logic natively in .NET. You literally get the raw power of custom code instead of just tweaking a rigid configuration file. All right, diving deeper. Section 4, data consistency and sagas. Before we even think about processing data, these distributed services have to actually find each other on the massive network. This client-side discovery flow shows you exactly how that plays out. A service wakes up, it registers itself, and then when another service needs to talk to it, it queries the registry for healthy instances. It picks one, maybe using a classic round-robin algorithm, and then makes the call directly to that IP. Think of service discovery as the dynamic, real-time address book for your entire architecture. But here's the really tricky part. What happens when those services start writing data? In a distributed setup, you might successfully save data to your local database, but then the network blips and you completely fail to notify the other services. That's a disaster. Enter the transactional outbox pattern. Look at this flow. Your API writes the business data and a notification message to an outbox table in one single atomic local transaction. Only after that local commit is 100% successful does a totally separate dispatcher process read that outbox and publish the event to your message broker. It literally eliminates the risk of losing messages in transit. And building directly on top of that outbox, we get the saga pattern. This is our epic coordination mechanism for stringing all those local database commits together across the network. Since we can't just lock databases across a dozen different microservices, a saga coordinates the whole dance. Each service does its local work, publishes an event, and triggers the next service in line. Eventually, step by step, you achieve eventual consistency across the entire system. It's brilliant. Next up, Section 5, Surviving Network Failures. So, we've got our gateway running, traffic is balancing, our data is syncing beautifully via sagas. But what happens when the physical network itself decides to fight back? First off, we have to fundamentally change our security mindset. We have to completely throw out this outdated legacy idea of a safe, internal, trusted network. Zero Trust networking treats every single request as a potential threat. In practice, that means we are authenticating every single service-to-service call based on strict identity and policy. You don't just get a free pass because your request came from a local IP address. Never trust, always verify. Which leads us to what is easily one of the most dreaded nightmare scenarios in all of distributed computing, the split brain. Picture this, your network partitions, and your once unified clusters splits into two totally isolated halves. Because they literally cannot talk to each other anymore, both sides just assume the other side is dead. So what do? They both elect a new leader. They both start accepting database rights independently. Suddenly, you have two active brains making conflicting, totally different decisions about your critical business data. That is a massive mess. And it's exactly why modern platforms demand incredibly strict consensus strategies, just to guarantee that only one brain remains active when the network inevitably snaps. And that brings us to our final section, Section 6, the Cloud Bedrock. Now, this slide lists essential Azure components, but let's take a step back and look at the absolute foundational bedrock of the cloud, specifically the AWS global infrastructure, because these architectural principles are totally universal. Before we design a virtual network or provision compute, we have to understand the physical ground we are building on. Let's be real for a second. Serverless is a lie. There are always physical servers, actual fiber optic cables, and massive power grids. Think of AWS like a massive global hotel franchise. A region, like US East 1 in Northern Virginia or EU Central 1 in Frankfurt, is a specific metropolitan area. Inside that region, you have availability zones, or AZs. An AZ is like a specific hotel building in that city. If one building's power grid fails or gets flooded, the other hotel across town, the other AZ, is completely fine. And then you have edge locations, which are like those tiny express kiosks at the airport. They don't have full compute servers, but they hold maps and brochures, caching static content via CloudFront so users get what they need instantly. Why does this matter? Because of physics. The speed of light is a hard limit, and data takes time to travel. Putting compute physically closer to users reduces latency. Plus, physical hardware fails. Earthquakes happen. Building on this global infrastructure completely eliminates the massive capital expenditure of buying real estate, negotiating with power companies, and laying ocean cables. You literally turn a global, disaster-proof data center deployment into a simple software API call. Let's look at an enterprise scenario. Say you're an architect building a global .NET e-commerce platform that needs 99.99% uptime. To comply with GDPR, you enforce that European user data stays strictly in the EU Central 1 region in Frankfurt. Data never leaves the EU. In the US, your .NET web APIs are spread across 3 availability zones in US East 1. If a hurricane absolutely destroys AZA, your application load balancer stops sending traffic there immediately. Autoscaling groups in AZ B and C automatically spin up new .NET containers to handle the load. And for your data, Amazon Aurora spans multiple AZs by default. If the master database in AZA dies, Aurora prompts a read replica to master in under 30 seconds. That is what true, unshakable cloud bedrock looks like. So once you truly understand those physical zones, you as the architect have to decide where your code actually lives on top of them. You basically have 2 paths. You can go with a hosted infrastructure, like Kubernetes. This gives you absolute deep control over the networking and the runtime environment, but you're paying for that infrastructure continuously, even when it's completely idle. On the flip side, you can go serverless using something like AWS Lambda or Azure Functions. Here, the cloud platform automatically scales your code without you managing any servers whatsoever, and you get pay-per-use pricing. It is absolutely perfect for bursty, event-driven APIs and background jobs. We have traced an amazing architectural journey today, from the user's very first entry at the API gateway through the complex maze of load balancers and sagas, all the way down to the physical, fiber optic cables of the cloud bedrock. So, I'm going to leave you with one critical, highly provocative question to evaluate your own systems right now. Is your current architecture truly resilient enough to survive a natural disaster and contain a split-brain scenario? Think about it. Thank you so much for joining me on this explainer, and keep